Across the observable universe, countless galaxies shine with their own internal logic, each one shaped by conditions that never repeat in quite the same way. Temperatures, radiation fields, stellar rhythms, chemical histories, gravitational patterns. Every galaxy is a different experiment in how matter can organize itself over billions of years. And if life ever emerged beyond our home, it would have risen within those unfamiliar settings, guided by rules we have never experienced. That is why our journey begins with a single question. Not where life is most likely, but where the laws of physics create opportunities we have not yet imagined. To answer it, we have to step beyond the Milky Way and examine other galaxies as potential environments, each with its own pathways for complexity to form, stabilize, and endure. Tonight we follow those paths outward, not to confirm what we already believe, but to uncover what the universe has been doing in all the places we have never seen up close. The first step in this exploration is recognizing how limited our home galaxy truly is as a reference point. The Milky Way tells only one version of how stars cluster, how elements circulate, and how radiation shapes planetary systems. Its history includes periods of violent star formation, long stretches of relative calm, and encounters with smaller galaxies that altered its structure. But many galaxies follow entirely different trajectories. Some ignite stars at frantic rates, flooding their environments with ultraviolet light that strips atmospheres from young worlds. Others evolve slowly, building heavy elements in quiet cycles that might give emerging chemistry enough time to organize. By comparing these varied environments, we begin to see that the conditions for life are not defined by a single recipe. They depend instead on the specific balance of processes inside each galaxy, and those balances shift dramatically as we move outward from our familiar corner of space. When we step beyond the Milky Way, the first galaxies we encounter reveal just how much variety exists in the structures that shape cosmic environments. Andromeda, for example, assembles stars at a slower rate than our own galaxy, producing a calmer radiation field in many of its mid-disk regions. That difference alone could influence the stability of atmospheres on young terrestrial planets. Triangulum, smaller and more energetic, fills large areas of its spiral arms with dense star clusters and supernova remnants, conditions that might accelerate the delivery of heavy elements while simultaneously disrupting fragile chemistry. Even the dwarf galaxies orbiting the Milky Way and Andromeda complicate our expectations. Some are nearly devoid of star formation, creating cold, dim environments, where any planetary heating must come from internal activity rather than starlight. Others form stars in brief bursts triggered by gravitational tides, producing environments that oscillate between long periods of silence and sudden flashes of intense radiation. These differences matter because life depends not only on the planets it inhabits, but also on the long-term behavior of its galactic surroundings. A stable region of moderate metallicity gives chemistry a chance to assemble complex molecules. Too much heavy element scarcity and planets may never gain the materials needed for tectonics or magnetic fields. Too much radiation and promising atmospheres may erode before biology takes root. As we examine the local group, we begin to see that each galaxy is a unique negotiation between gravity, chemistry, and time. Some will offer windows of stability that last billions of years. Others will present only brief opportunities before their internal dynamics shift into more hostile phases. And yet, despite their differences, these galaxies offer something the Milky Way cannot provide by itself: a comparative data set. By studying their star formation, histories, elemental distributions, and structural evolution, we gain the ability to identify which galactic traits foster long-term biochemical potential. We learn to ask whether calm, slowly evolving systems are more promising than active ones filled with stellar nurseries. We learn to recognize which regions of a galaxy are inherently unstable, and which might preserve planetary environments long enough for biology to gain complexity. In this early stretch of our journey, the patterns emerging across these nearby galaxies remind us that life is not only a planetary question, it is a galactic one dictated by processes that unfold on scales far larger than any world a living organism will ever see. As we push farther into this survey, a clearer pattern begins to form. Not every region inside a galaxy offers the same chance for life to endure. Astronomers call this the galactic habitable zone, a band where conditions remain stable enough for planets to keep their atmospheres, and for chemistry to evolve over immense spans of time. Near the centre of a spiral galaxy, stars crowd together in dense clusters. Radiation levels are high, supernovae are frequent, and the gravitational tides from the central black hole reshape orbits in ways that can destabilize planetary systems. Even if planets exist there, they must endure a constant cycle of energetic events that strip atmospheres or sterilize surfaces before complex molecules can build themselves into anything long-lasting. Far out on the edges of a galaxy, the situation reverses. Space becomes quiet, but heavy elements grow scarce. Planets may form, but without enough metals to create strong magnetic fields or layered interiors, they struggle to maintain stable climates. Many could become cold, barren spheres where little chemistry can progress beyond simple reactions. It is only in the middle regions that the balance becomes favourable. Here the star density is moderate, heavy elements are abundant enough for rocky planets to form, and supernova rates are low enough to avoid constant disruption. The Milky Way's own habitable zone occupies this middle band, but that pattern repeats across other spiral galaxies as well. What changes from one galaxy to another is the width and character of this zone. Andromeda's habitable band stretches wider than ours, shaped by its slower star formation rate, and the distribution of older stellar populations. Its central region is active, but not as intensely as the Milky Way's, and its outskirts contain enough metals to support rocky planets farther out than expected. In contrast, Triangulum's habitable zone is narrower, compressed by regions of rapid starbirth that inject powerful radiation into the surrounding medium. Even dwarf galaxies show hints of their own zones, though their small size means that any promising region may shift as gravitational interactions reshape their structure. Recognizing these galactic-scale patterns reshapes how we think about the search for life. Instead of treating each galaxy as a single environment, we begin to see internal neighborhoods with different long-term prospects. Some will remain stable for billions of years, others will drift through phases of intense turbulence. This perspective prepares us for the next stage of our journey, where we look beyond the structure of galaxies themselves and examine the stars inside them, identifying which types offer the best foundation for planets where life could take hold and endure. As we move from the structure of galaxies to the stars inside them, the search becomes more precise. Not every star provides the long, stable environment needed for life to unfold. Many burn too brightly and die too quickly, flooding their surroundings with radiation before any planet has time to develop a stable climate. Others flicker unpredictably, releasing powerful flares that strip atmospheres from nearby worlds. The key lies in identifying stars that remain calm for billions of years, allowing chemistry the patience it needs to become something more. In our own galaxy, stars similar to the Sun are often seen as ideal. They produce steady light, maintain stable fusion for long periods, and create regions where temperatures support liquid water on rocky planets. But stars like these are not the most common. Across every spiral galaxy we've studied, the majority of stars are small, cool red dwarfs. Their lifespans stretch far longer than the age of the universe itself, offering timeframes where biological evolution could proceed without interruption. Yet they come with their own challenges. Many red dwarfs emit intense flares in their early phases, potentially sterilizing young planets. Others lock their planets into slow rotations where one hemisphere faces perpetual daylight while the other remains in darkness. Whether these conditions help or hinder life is still an open question. Larger galaxies like Andromeda contain even more diverse stellar populations. Their outer regions hold old metal-poor stars that formed early in cosmic history. Their inner regions host younger stars with richer chemical content, providing the building blocks for complex planets. Triangulum, by contrast, produces stars at a faster pace, filling its arms with energetic clusters, where planets may form quickly, but must endure high radiation levels. Each of these stellar environments teaches us something different. It shows us that the potential for life depends not only on the galaxy as a whole, but on the specific mixture of stars within it. By comparing these stellar populations, a pattern emerges. Long-lived stars with moderate radiation output are the most promising. They provide steady illumination, stable gravitational fields and planetary systems, where climates can remain consistent for enormous stretches of time. When we map these stars across different galaxies, we begin to see pockets where the balance is right. These pockets are not evenly distributed. Some galaxies host vast regions where calm, stable stars cluster together. Others concentrate their suitable stars into narrow bands where conditions briefly align. This realization pushes our journey forward. Finding the right stars is only part of the challenge. The next step is understanding the planets that orbit them and estimating how many worlds might offer the right ingredients for life. With what we know about exoplanets in the Milky Way, we can begin to extrapolate outward, constructing a picture of what planetary systems in distant galaxies might look like and where life could plausibly begin. With the right stars in view, the next question is how many planets orbit them and what kinds of worlds those planets might be. Inside the Milky Way, our surveys have revealed a simple but transformative fact. Planets are not rare, they are the default outcome of star formation. Nearly every star we observe appears to have at least one planet, and many host entire families of worlds arranged in patterns more varied than anything we once imagined. Rocky planets the size of Earth are common. Super-Earths with thick atmospheres, warm ocean worlds, and unstable volcanic planets appear throughout our galactic neighborhood. Hot Jupiters circle close to their stars while chains of small planets move in tight, well-aligned orbits. These findings give us a foundation for extending the search beyond our own sky. Even though we cannot directly detect planets in other galaxies with current instruments, the laws governing planet formation remain the same. Protoplanetary disks form around young stars regardless of which galaxy they inhabit. Dust grains collide and merge, creating planetesimals that build into full worlds through slow, persistent accumulation. The distribution of heavy elements inside a galaxy will influence the types of planets that form, but not the fundamental mechanics. That means spiral galaxies with rich stellar populations are likely to host trillions of rocky planets. Elliptical galaxies filled with older stars and fewer metals may generate fewer terrestrial worlds, but still support long-term stability for any planets that do form. Even dwarf galaxies, though small, produce compact planetary systems around their quieter stars. The challenge is imagining how these planetary systems behave under different galactic environments. In regions with high radiation atmospheres may change rapidly, creating a shifting landscape of chemistry. In calmer regions, planets might retain thick atmospheres for billions of years, enabling slow but steady chemical evolution. Some worlds could orbit in wide, stable paths far from dangerous stellar events. Others might endure cycles of disruption and recovery, forcing any potential biology to adapt to rapid environmental change. These possibilities multiply as we consider the immense number of stars inside each galaxy. Even a conservative estimate suggests that the local group alone contains trillions of planets. Most will be cold, barren, or unstable, but a fraction will fall into the narrow range where habitability becomes plausible. The more we compare galaxies, the more this fraction seems inevitable. With so many planetary systems forming under such a wide variety of conditions, it becomes difficult to imagine that only our own galaxy produces worlds with the right temperatures, materials, and stability for chemistry to become complex. Instead, the statistical weight points toward abundance. Life may not simply be possible in other galaxies. It may be common emerging whenever a planet remains stable long enough for chemistry to organize. And as our journey extends beyond the local group, we find that the cosmic environments shaping these worlds grow even more diverse, pushing us toward regions where the large-scale structure of the universe becomes a key part of the story. As we move beyond the local group, the universe begins to reorganize itself on scales far larger than the individual galaxies. Here, galaxies are no longer solitary objects drifting through empty space. They gather into clusters bound by gravity, stretch into enormous filaments, and leave behind vast regions of near-emptiness known as cosmic voids. These structures form the scaffolding of the observable universe, and each one creates a different environment that could influence where life might arise or endure. Galaxy clusters are the first major milestone in this journey. Massive structures like the Virgo or Coma cluster contain thousands of galaxies packed into relatively close quarters. Their intracluster medium glows with diffuse superheated plasma, emitting high-energy X-rays. This environment is extreme compared with the calm regions of the Milky Way. Interaction between galaxies is more common. Some lose their gas as they move through the dense intracluster medium, shutting down star formation entirely. Others collide, triggering bursts of new stars that illuminate the surrounding space with ultraviolet radiation. For life, these clusters are a paradox. They contain immense numbers of stars and planets, far more than any single galaxy, yet they also present a dynamic and sometimes hazardous setting, where long-term stability may be difficult to maintain. Even so, pockets of calmer regions within clusters may shelter planets for billions of years, especially in galaxies that orbit far from the chaotic core. Filaments create a different kind of environment. These colossal strands of galaxies stretching hundreds of millions of light-years form the connective tissue of the cosmic web. Conditions within filaments vary widely. Some areas host active galaxies rich in star formation. Others remain relatively quiet, shaped by their distance from dense cluster centers. Because filaments span such enormous scales, they offer a spectrum of possibilities for habitability. A galaxy positioned along a tranquil segment of a filament might experience fewer disruptive interactions and maintain a consistent supply of gas for building stars. In these more stable regions, the long arcs of cosmic time create opportunities for planets to evolve without the constant threat of radiation bursts or gravitational upheaval. Then there are the cosmic voids. These regions are often misunderstood as empty, but they contain galaxies too scattered sparsely across vast expanses. Life in a void would unfold under entirely different conditions. With fewer nearby galaxies, the external radiation environment is often quieter. Supernovae are rare. Disturbances from neighbouring galaxies are minimal. The trade-off is that void galaxies typically contain fewer heavy elements, which may limit the formation of complex terrestrial planets. Even so, the quietness of these environments raises an interesting possibility. If life requires long periods of uninterrupted stability, then void galaxies may offer a subtle advantage. They may not produce many habitable worlds, but the ones that do exist could remain stable for longer than planets in more crowded regions. Taken together, clusters, filaments and voids remind us that the search for life is not confined to a single type of cosmic neighbourhood. Each structure shapes the evolutionary path of its galaxies, influencing which stars form, how planets develop, and how often environments remain undisturbed. And as we continue outward, we encounter galaxies whose shapes and histories break the usual patterns, revealing new and unexpected opportunities for life to take root. As our path carries us deeper into the cosmic web, the orderly spirals and calm ellipticals give way to galaxies whose shapes and histories defy simple expectations. These unusual systems force us to reconsider what environments might sustain life, because many of them operate under physical conditions far removed from those in the Milky Way. Some are shaped by collisions that tore their structure apart and reassembled it into new forms. Others contain rings of bright stars created by precise gravitational interactions. Still others ignite enormous starburst events that turn entire regions into laboratories of rapid stellar evolution. Ring galaxies are among the most striking examples. They often form when a smaller galaxy plunges directly through the disk of a larger one, sending a wave of compressed gas sweeping outward like the ripple from a dropped stone. That expanding ring triggers intense star formation along its edge, creating luminous arcs that span tens of thousands of light years. Conditions inside these rings are harsh. Young massive stars flood the surrounding space with ultraviolet radiation, and supernova explosions arrive in frequent succession. Yet beyond the ring itself, the inner regions of the galaxy can become unusually calm. Gas that once filled the central area may be cleared out, reducing the number of disruptive stellar events. If stable stars with long lifetimes inhabit these quieter zones, they could play host to planetary systems unaffected by the turbulence along the ring. Interacting galaxies offer a different picture. When two galaxies pass close enough to distort each other's shapes, their gravitational forces can funnel gas toward their centers, ignite bursts of star formation, and reshape entire spiral arms. These processes occur over millions of years long compared to a human lifetime, but short on the scale of cosmic evolution. For life, such interactions introduce both risk and opportunity. Regions undergoing rapid change may become inhospitable, but the redistribution of gas can also create new stable zones where planets can form with an enriched supply of heavy elements. In some cases, interactions even trigger the formation of extended tidal tails, where small compact star clusters emerge from the displaced material. These clusters might contain stars calm enough for long-term biological processes, isolated far from the energetic cores of the interacting galaxies. Starburst galaxies represent the extreme end of this spectrum. Their star formation rates exceed those of typical spirals by large factors, generating clusters filled with young, massive stars that burn brightly and die quickly. Radiation levels in these environments are intense, and the high number of supernovae can make them seem incompatible with habitability. But starbursts do not last forever. They are short, dramatic episodes in the life of a galaxy. As the burst subsides, the remaining gas settles into new configurations, sometimes producing regions where older stable stars dominate. The metals forged during the burst enrich the surrounding interstellar medium, increasing the likelihood that planets with strong magnetic fields and complex geology can form in the future. These unusual galaxies highlight an important lesson. The potential for life is not limited to systems that resemble our own. Even environments shaped by violent events may create brief windows of stability or long-term niches where life can develop if given enough time. The diversity of galactic behavior across the universe means that habitability is not a single condition, but a spectrum shaped by history structure and the slow transformations that unfold over billions of years. And as we move beyond these familiar forms, we begin to confront an even more profound question. What happens to the search for life when the underlying physics of a galaxy does not match the rules we take for granted? Beyond the familiar behavior of ordinary galaxies lies a possibility that forces us to rethink what a cosmic environment can be. We assume that every star, every cluster, and every spiral arm follows the same physical constants that shaped our own galaxy. But the laws we observe may represent only one configuration among many. If the broader multiverse contains regions where the strengths of certain forces differ slightly, then entire galaxies could form under conditions that would feel foreign to anything in the Milky Way. Consider a universe where gravity is marginally stronger. Stars would collapse more easily, reaching higher densities before stabilizing. Their lifetimes would shorten, and planetary orbits would need to sit farther out to avoid being engulfed. Chemical elements might fuse more readily, altering the periodic table itself. In such a galaxy, rocky planets could remain rare while massive gas envelopes dominate most worlds. Life, if it formed at all, might emerge within dense atmospheric layers rather than on solid surfaces. Shift gravity in the opposite direction, and everything stretches outward. Stars swell into diffuse objects with lower temperatures. Fusion becomes harder to sustain. These stars could live for extraordinary lengths of time, but their light would be faint and heavily shifted toward the infrared. Any life that depends on stable illumination might develop extremely slowly or rely on energy sources unrelated to starlight. Under these dim conditions, planetary chemistry would resemble a slow-motion experiment unfolding across billions of years. Other constants introduce even stranger outcomes. If the electromagnetic force was slightly weaker, atoms would bind differently. Molecules we take for granted might never form, while new forms of matter with unusual stability would take their place. In that scenario, planets might develop crusts with crystalline frameworks unlike anything seen on Earth. Energy could move through these networks in patterns that behave almost like biological signaling, raising the possibility of life built not from cells, but from structured lattices that store and process information. Even the speed of light plays a role. A slower maximum speed alters how heat moves through planetary atmospheres and how radiation interacts with matter. Galaxies built under this rule would evolve at a gentler pace. Stellar flares would propagate more gradually, giving planets more time to adapt. A faster speed of light does the opposite, creating a cosmos where temperature shifts and radiation bursts sweep across systems with little delay. Any organism or self-organizing structure in such an environment would need to react quickly, making adaptation a matter of rapid response rather than slow evolution. These variations are small on paper, yet produce galaxies with entirely new architectures. Some would host long-lived environments where complexity has ample time to develop. Others would create volatile settings where stability is rare but innovation could arise through extreme conditions. The search for life in these exotic galaxies becomes less about identifying familiar patterns and more about understanding which combinations of physical rules allow complexity to persist. That shift opens a new frontier in our journey, one where life may emerge not from matter as we know it, but from the deeper logic encoded in the laws that govern each universe. Within these altered physical landscapes, the concept of life begins to move beyond the familiar boundaries of molecules and cells. When the rules that shape atoms shift, the definition of a living system shifts with them. In some universes, matter may not assemble into stable molecules at all, yet complexity can still arise if energy flows settle into patterns that persist, adapt, and respond to their surroundings. Under those conditions, life becomes an expression of organization, not chemistry. Imagine a galaxy where plasma remains stable at much lower densities than in our universe. Large magnetic structures could form inside nebulae, looping and twisting for millions of years without dissipating. Within those currents, charged particles might arrange themselves into long-lived configurations capable of transporting information. These formations would have no surface, no interior, no metabolism in the biological sense. Their identity would be defined by the rhythm of electromagnetic waves moving through them. A change in surrounding radiation could alter those rhythms, prompting behaviors that resemble adaptation. Other possibilities emerge in environments where exotic matter dominates. If dark matter interacts weakly, but not negligibly with itself, dense clumps might form intricate gravitational webs. Any fluctuation inside those webs could propagate like a signal encoding information in subtle shifts of mass distribution. Over vast time spans, these structures might learn to maintain stable patterns by adjusting their internal balances, creating a form of existence supported not by atomic bonds, but by gravity itself. In such a system, the equivalent of growth would be the expansion of the web. The equivalent of memory would be the persistence of repeating oscillations. There are also scenarios shaped by variations in the nuclear forces. If certain reactions release energy in predictable cycles, regions of space could develop pulsing fields with stable phases. These pulses might synchronize naturally forming networks that behave collectively. A slight disturbance could ripple outward and provoke a coordinated response similar to how neurons fire in a biological brain. But here the cells are regions of oscillating energy, and the brain is a cloud of pulses spread across a significant portion of a galaxy. Even the geometry of space-time can support unusual forms of order. In universes where curvature behaves differently, standing waves may settle into long-lived configurations. These waves could interact in ways that allow them to store and transform energy with surprising efficiency. If such configurations discover stable feedback loops, they may evolve into patterns capable of sensing changes in their environment and adjusting their structure accordingly. This would be life built not from matter, but from geometry, arising wherever the curvature of space allows complex vibrations to persist. None of these forms resemble the biology we know, yet all share the same fundamental requirements. They maintain structure over time. They draw energy from their surroundings in ways that preserve that structure, and they alter themselves in response to external conditions. If the multiverse truly contains galaxies shaped by unfamiliar physics, then these kinds of entities may represent the natural outcome of those environments. They may not breathe, metabolize, or reproduce as life does here, but they could still carry identity function, and perhaps even forms of awareness. In any universe, the moment complex structures begin to persist, the door to evolution opens. Stability alone is not enough. There must also be variation feedback and the capacity to respond to changing conditions. But when the underlying physics shifts, the pathways through which evolution unfolds become radically different. Processes that shape life here may not apply at all, while mechanisms that are impossible in our universe could dominate elsewhere. Consider environments where stars live far longer than the Sun. In those places, the timescale for environmental change stretches out enormously. A planet might remain stable for tens of billions of years, giving any primitive system almost endless opportunities to refine itself. Evolution there would not rely on rapid mutation cycles, but on slow chemical or structural adjustments, accumulating over unimaginable spans of time. A single adaptive step could take millions of years, yet still be meaningful within such a vast window of stability. In galaxies governed by stronger radiation fields, the opposite happens. Conditions shift quickly. Energy sweeps across planetary systems in surges rather than gentle gradients. Under these circumstances, any organism or organized structure must rely on rapid transformations to survive, instead of slow, genetic variation. The primary mechanism for adaptation could be the rearrangement of internal energy flows, structural reconfiguration, or the ability to enter dormant states. Evolution becomes a matter of resilience rather than precision, rewarding systems that can rebuild themselves after each disruptive event. Exotic forms of matter introduce additional possibilities. A crystalline network capable of transmitting energy pulses might evolve by altering its internal lattice, expanding or contracting specific regions to improve stability. Over time, these networks could gain the ability to propagate signals, correct structural flaws, or coordinate responses across large areas. In such a universe, reproduction might not involve creating offspring, but rather extending the network into new territory. The equivalent of natural selection would arise from competition between different patterns of energy transmission, with the most stable or efficient ones persisting. In a cosmos where plasma structures dominate, evolution could occur through changes in magnetic topology. A loop of charged particles might split, merge, or reconfigure itself depending on the surrounding environment. Any arrangement that preserves cohesion and responds effectively to disruptions would stand a better chance of surviving. Over millions of cycles, these loops could develop stable modes of oscillation that function like inherited traits. Even the geometry of space can shape evolution. If curvature fluctuates on small scales standing, waves might adapt by shifting their nodes and antinodes to maintain stability. Disturbances would propagate through these wave pattern entities, much like sensory input prompting them to adjust their configuration. Those that fail to adapt would dissipate. Those that succeed would form the foundation for more intricate behaviors. Across these scenarios, one theme remains constant. Evolution finds a path wherever complexity can endure. It does not depend on carbon, water, DNA, or the temperatures and pressures familiar from Earth. It depends only on rules that allow structures to persist long enough for variation and adaptation to matter. This makes the search for life in alternate galactic environments far broader than we once imagined. It transforms the question from could other planets host biology, to which cosmic settings allow complexity to refine itself over time, and that question leads directly to the possibility of intelligence emerging under laws that differ from our own. Nothing restricts intelligence to the biological form we know. Once evolution has a mechanism for building complexity, awareness becomes a possibility wherever information can be stored, transmitted, and acted upon. In the Milky Way, neurons accomplish this through electrical impulses and chemical gradients, but other galaxies operating under different physical conditions could nurture entirely different platforms for cognition. In a universe where crystalline structures dominate, intelligence might arise as patterns of energy traveling through vast mineral frameworks. A signal could move along branching channels, encounter intersections, and choose pathways based on variations in temperature, pressure, or ambient radiation. Over long periods, these networks could reorganize themselves to improve stability and efficiency. With time, a distributed consciousness might emerge not as a cluster of cells, but as a vast interconnected geometry. Such an entity would not perceive the world through senses, It would detect shifts in environmental fields directly with awareness emerging from the cumulative changes rippling across its structure. Energy-based systems offer a different route. Plasma loops bound by magnetic fields could behave like self-modifying logic circuits. A disturbance in one region might propagate to others, prompting new configurations. If these loops develop stable routines that interpret conditions and adjust accordingly, a rudimentary intelligence could follow. Over millions of cycles, the loops might discover strategies for maintaining coherence in turbulent environments. Awareness in this case would be the ability to anticipate patterns in the surrounding plasma and respond before instability sets in. Dark matter presents another speculative channel. Although dark matter rarely interacts with ordinary matter, it might interact with itself. If so, dense regions could form structures through gravitational resonance. Oscillations within these structures might act as information carriers. If feedback mechanisms allow them to adjust to external influences, then a form of thought could arise invisible to any observer using conventional instruments. Such minds might perceive the universe only as gradients in gravitational potential, interpreting patterns we cannot detect. Even space-time itself could host intelligence under the right conditions. If curvature in some universes supports stable standing waves, those waves might encode information in their vibration modes. A shift in curvature could alter those modes, and the system might adapt by reconfiguring its internal pattern. Over sufficiently long periods, this process could grow more sophisticated. Communication between wave structures could produce collective behavior resembling a shared consciousness spread across light years. These possibilities challenge every assumption about what intelligence must look like. It may not rely on body senses or a single localized brain. It might not age or reproduce. Its perception of time could differ radically from ours. A plasma intelligence might think in cycles measured in milliseconds, while a gravitational one could take centuries to complete a single deliberation. Some forms might be entirely unaware of us, because their mode of perception aligns with forces we cannot directly observe. The search for intelligence in other galaxies therefore becomes a question of which environments allow information processing structures to take shape and persist. And that question leads us back toward our own understanding of life, prompting us to reconsider whether our definition is too narrow. If intelligence can arise wherever physics permits complex feedback, then the universe or the multiverse may be filled with minds we're not equipped to recognize. Reaching the far edge of our imagined journey forces us to turn back toward a more intimate question. After considering galaxies built from unfamiliar physics life that requires no molecules and intelligences, whose perception of time or matter diverges entirely from ours, what does this exploration say about our own place in the cosmos? The Milky Way begins to feel less like a template for existence, and more like a single expression drawn from a vast set of cosmic possibilities. Everything familiar, our chemistry, our biology, our consciousness, emerges from one particular combination of constants and conditions. Shift those values and new forms of order follow. Some would dissolve quickly. Others might stabilize into structures more resilient than anything Earth has produced. This perspective changes how we interpret our search for life. Instead of asking whether another world hosts organisms resembling those on Earth, we begin to ask which environments support the self-organization of complexity, regardless of its physical substrate. Even small differences in stellar activity, galactic structure, or underlying constants could steer evolution toward outcomes that lie outside all our expectations. A planet in a quiet dwarf galaxy might nurture slow, deliberate forms of cognition that treat time as a nearly static resource. A plasma intelligence drifting through a high-energy nebula could experience its world as a continuous flow of currents and fluctuations. These possibilities emphasize that intelligence is not tied to a single design, but to the broader capacity for information to accumulate and adapt. Turning this idea back on ourselves reveals something important. Life on Earth is not fragile simply because it relies on water and carbon. It is fragile because it relies on a very narrow fit between environmental conditions and biological mechanisms. When we compare that narrowness to the range of environments across the universe, our existence becomes a rare intersection of stability, chemistry, and time. But rare does not mean unique. It simply means that our version of life occupies one solution space among many others permitted by physics. What stands out most after surveying these cosmic possibilities is not how unusual our world is, but how many different routes the universe might offer for complexity to arise. Whether built from atoms, plasma lattice structures, or curvature itself, complexity follows from rules that encourage persistence and variation. Those rules appear repeatedly across nature. They shape river networks, crystal growth, atmospheric patterns, and the neural activities inside human brains. The underlying mathematics shows up in systems large and small, suggesting that the universe may be predisposed to generate structure wherever conditions allow. This broader view does not diminish the significance of Earth. Instead, it highlights the remarkable outcome of one cosmic experiment, while reminding us that countless others may be running in parallel, hidden behind the glare of distant galaxies, or sealed within universes governed by altered constants. We may never encounter these alternate forms directly. Their senses, timescales, or material foundations might make communication impossible, but acknowledging their potential reshapes how we see ourselves. Rather than occupying the center of a lucky arrangement, we become participants in a much larger set of possibilities, a single branch in an expanding landscape of cosmic expression. Our journey across these imagined galaxies therefore ends not with answers, but with perspective. The universe, and perhaps the multiverse, may be filled with environments where complexity takes forms we have yet to conceive, and the only reason we can imagine them at all is because our own corner of existence produced minds capable of asking how many other ways reality might choose to organize itself. For now, our exploration of life across galaxies and beyond familiar physics reaches a natural pause. We have traced the limits of what matter, energy, and even space-time might allow. But there is one question still hanging over everything we've imagined. If life can take so many forms and evolve under so many rules, then what shapes the environments where these possibilities begin? The structure of a universe does not emerge at random. Something sets its constants, its expansion, its temperature, history, and the pattern of galaxies that later become homes for stars and planets. To understand why life may appear in some realities and not in others, we need to step even further back and examine the origins of the cosmic frameworks that make life possible in the first place. From the moment the universe became transparent, something remarkable was already true. The laws that shape everything we see, the strength of gravity, the charge of the electron, the rate at which space expands, had settled into values so specific, so narrow, that matter could cool, stars could ignite, and worlds could eventually form. These numbers did not drift. They did not fluctuate. They locked into place with a precision that leaves almost no room for error. Change any one of them even slightly and the universe we know collapses. Stars fail to burn. Atoms refuse to bind. Time stretches without structure. Space fills with nothing but light and plasma. The cosmos becomes silent, inert, incapable of building even the simplest complexity. Yet in our universe, everything aligns. Hydrogen survives long enough for fusion to begin. Carbon appears through a delicate nuclear resonance. Galaxies assemble under a gravitational balance so exact that it borders on improbable. We rarely notice this because the laws feel inevitable, but they are not. They are conditions set once under which all future possibilities unfold. And the question that emerges from this realization is not abstract. It cuts directly into the foundation of existence. Why do the laws of nature permit life at all? Why do they fall into the tiny range where structure, chemistry, and consciousness can arise? What we see around us is only one version of what reality could have been. To understand why our universe allows life, we must trace each rule back to the beginning, examine how narrow the margins truly are, and confront the possibility that these laws are not universal, but selected from a deeper landscape of possibilities we have yet to map. The first step in understanding this problem is recognizing how little margin the universe gives us. Every structure we rely on, from atoms to galaxies, exists only because a network of physical parameters sits within a narrow window of stability. These parameters are not decorative. They determine how matter behaves, how forces interact and how energy moves through space. If any one of them had landed outside its viable range, the universe would still expand and evolve, but not into a form capable of supporting stars, planets, or living chemistry. Gravity illustrates this with intimidating clarity. Its strength is astonishingly weak compared to the electromagnetic force. Yet this weakness is precisely what allows stars to burn slowly instead of collapsing instantly. If gravity were only slightly stronger, stars would burn through their fuel in moments measured on cosmic timescales, brief flashes rather than long-lived furnaces. If gravity were weaker, gas would fail to collapse at all, preventing stars from forming in the first place. The difference between a universe filled with light and one filled with darkness is measured in a range so narrow that it borders on unimaginable. The same is true for the strong nuclear force. This force binds protons and neutrons together inside atomic nuclei. Increase its strength just a little, and almost every proton would lock onto another, erasing hydrogen, the element that fuels stars and forms water. Reduce it slightly and nuclei could not hold themselves together. The periodic table would collapse to little more than hydrogen and helium, leaving no building blocks for the chemistry of life. Even mass ratios play a decisive role. The electron's mass relative to the proton determines the structure of atoms. Adjust that ratio and atomic energy levels shift, altering how elements bond. Chemistry as we know it depends on this ratio remaining extraordinarily stable. Without that stability, complex molecules could never assemble, and life's information-carrying systems would have no platform on which to operate. These examples point to a deeper pattern. The laws of nature appear calibrated for the emergence of long-term complexity. The universe is not friendly to life by default. It is friendly only because a delicate balance of forces permits systems to persist long enough to evolve. Stars provide steady energy. Molecules remain stable. Planets hold atmospheres. None of this occurs without an extraordinary alignment of parameters set in the earliest moments of cosmic history. This realization shifts the question. Instead of wondering whether life is common, we begin to ask why the underlying framework of the universe makes life possible at all. What determine the values of these constants? Are they fixed and immutable, or are they outcomes of deeper processes that could have selected entirely different numbers? And if different numbers were possible, how many other universes, real or hypothetical, would fail to ignite even a single star? To explore these questions, we must examine the architecture of physical law itself, and uncover how tightly the existence of everything depends on the values chosen at the beginning. To understand why the universe permits complexity, we need to look closely at the framework that governs every interaction. Physical law is not a collection of abstract equations floating above reality. It is the operational blueprint that determines what kinds of structures can exist. The forces, constants, and symmetries embedded in this blueprint act together to define the entire range of possible behaviors in the cosmos. Change the blueprint and the universe follows a different trajectory from its first moments onward. At the foundation lie four fundamental interactions: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. Each governs a specific domain, and life depends on all four working in concert. Gravity shapes the large-scale structure of the universe, gathering matter into stars and galaxies. Electromagnetism controls chemistry, determines how atoms bond, and enables the flow of energy within biological systems. The strong force holds atomic nuclei together, and the weak force allows the fusion reactions inside stars to proceed at just the right rate. None of these forces can drift without consequence. Together they form a system of remarkable precision. Alongside the forces sit a series of dimensionless constants numbers that do not depend on units, and therefore reveal the intrinsic structure of reality. The fine structure constant dictates the strength of electromagnetic interactions. The proton-to-electron mass ratio sets the scale of atomic patterns. The cosmological constant determines how fast space accelerates outward. These numbers appear arbitrary, yet they shape everything from the stability of atoms to the distribution of galaxies across the sky. If the fine structure constant were even a little larger, electrons would bind too tightly to nuclei, making chemical reactions sluggish or impossible. If it were smaller, atoms would have difficulty maintaining coherent structures. Chemistry itself would collapse. Another crucial ingredient is the shape of the potential fields that define particle behavior. Some of these fields determine the masses of elementary particles' masses that influence how particles decay, how they combine, and whether they form long-lived states. Alter those masses slightly, and the universe could end up with no neutrons, no stable hydrogen, or no heavy elements. These tiny shifts propagate outward, changing stellar evolution and suppressing the formation of planets. Symmetries also play a decisive role. The fact that the laws of physics do not change from place to place or moment to moment is not a trivial observation. It is a deep structural property of the universe. Break that symmetry and conservation laws like conservation of energy or momentum begin to fail. Without these conservation systems cannot maintain order or build long-term stability. Evolution, whether physical or biological, depends on stable rules. Without consistent laws, patterns cannot accumulate and complexity dies before it begins. Even the vacuum itself, seemingly empty space, has parameters that influence what kinds of universes are possible. The energy of the vacuum sets the overall curvature of space. If that energy were higher, the universe would expand so rapidly that matter could never condense. If it were lower, gravity would eventually reverse the expansion, causing everything to recollapse. The actual value sits in a narrow band where galaxies can emerge, persist, and enrich themselves over billions of years. This architectural balance is not a coincidence we fully understand. It is a set of interconnected conditions that enable stability at every scale. Forces bind matter. Constants establish patterns. Symmetries preserve order. Each layer supports the next, creating a chain that stretches from the quantum realm to the cosmic web. Break the chain at any point and the universe loses its capacity to produce structure. Recognizing this interconnectedness brings us closer to the heart of the fine-tuning puzzle. The laws of nature are not just precise, they are coordinated. They form a system in which the viability of stars, planets, and chemistry depends on relationships that appear extraordinarily tight. Why they take these values and not others becomes the central question as we move deeper into the early universe. To trace the origins of fine-tuning, we must return to the earliest moments of the universe, when the laws and constants we observe today first settled into place. In that initial fraction of a second, the cosmos underwent a transformation so rapid and so sensitive to initial conditions that even the slightest deviation would have altered the trajectory of everything that followed. This is where the question grows sharper. Why did the universe begin in a state that allowed matter structure and eventually life to emerge? The expansion rate at the beginning illustrates the precarious balance at work. Immediately after the Big Bang, space stretched outward at a speed determined by a competition between matter density and the energy driving expansion. If the universe had expanded even slightly faster, matter would have thinned too quickly to form galaxies. Hydrogen and helium would drift apart before gravity could gather them into stars. On the other hand, if expansion had been slower by the smallest fraction, gravity would have overwhelmed the outward push, causing the universe to collapse back into a dense hot state before the first atoms could form. This is not a loose tolerance. Calculations show that the permissible range in the early expansion rate is astonishingly small. The balance between gravitational attraction and cosmic acceleration must be tuned to something like 1 part in 100,000 billion. A shift of a few decimal places in either direction leaves a universe without stars, planets, or chemistry. Yet the universe we inhabit followed the narrow path between these extremes. The matter distribution was another critical factor. Small fluctuations in density seeded the growth of galaxies. These variations had to be large enough for gravity to amplify them, but not so large that the early universe fragmented into dense clumps collapsing into black holes. If the fluctuations were smaller, the universe would remain smooth with no structure forming at all. If larger gravitational collapse would dominate, leading to a cosmos filled with isolated dark regions devoid of stable environments, the temperature of the early universe also played a decisive role. As the cosmos expanded and cooled, it passed through narrow windows where atoms could form without being immediately torn apart by high-energy photons. If cooling had occurred too slowly, the universe would stay ionized for too long, delaying structure formation. If too quickly, the formation of atoms would occur before density variations had grown sufficiently again, preventing galaxies from taking shape. Even the balance of matter types mattered. Dark matter, although invisible, provided the gravitational scaffolding needed for galaxies to assemble. Too little dark matter and gas would not gather quickly enough. Too much and galaxies would become overly compact and hostile to stable planetary orbits. The observed ratio falls within a surprisingly narrow range that permits large-scale structure without overwhelming the spaces between stars. Each of these conditions alone would be remarkable. Together they outline a universe that appears to have unfolded along a razor-thin trajectory, one that permitted neither runaway collapse nor runaway expansion. The early cosmos navigated this landscape with a precision that continues to puzzle physicists. What determined these initial values? Were they selected emergent or simply brute facts? Understanding this early balance is crucial because it set the stage for everything that followed. The ignition of the first stars, the creation of the heavy elements, the assembly of galaxies, and eventually the possibility of life. To continue unraveling the story, we must turn to one of the most delicate requirements of all, the formation of long-lived stable stars. Stable stars are among the most improbable outcomes of the physical laws we inherited. They look simple from a distance, glowing spheres burning quietly in the dark, but the conditions that allow a star to shine steadily for billions of years occupy an incredibly narrow region of parameter space. If the forces governing matter were altered even slightly, stars would behave very differently, and many universes would never experience anything resembling long-term illumination. A star's stability depends on a delicate equilibrium between two opposing effects: the inward pull of gravity and the outward push created by nuclear fusion in its core. Gravity tries to compress the star while fusion releases energy that counters the collapse. In our universe, this balance is self-regulating. If the core becomes slightly hotter, fusion accelerates, increasing outward pressure and preventing runaway heating. If it becomes cooler, fusion slows, gravity gains ground, and the core contracts until temperature rises again. This automatic thermostatic behavior hinges on precise relationships between the strengths of the fundamental forces. If gravity were modestly stronger, this feedback mechanism would break down. Stars would compress to higher pressures, igniting fusion at rates far above what we see in the Sun. Their lifetimes would shrink dramatically, millions of years instead of billions. That span is far too short for complex chemistry to develop on surrounding planets. Life needs time to refine information, and massive stars in a high-gravity universe would burn too fast for anything stable to arise. If gravity were weaker, gas clouds would struggle to collapse at all. Many would disperse before reaching the temperatures needed for fusion. Those that did form stars would tend to produce vast diffuse objects incapable of sustaining the fusion cycles required for carbon, oxygen, and other life-essential elements. The galaxy might contain glowing nebulae and scattered pockets of heat, but few true stars. The strong nuclear force adds another layer of constraint. This force governs how nuclei bind within stars and determines which fusion chains are possible. If the strong force was slightly stronger, fusion reactions would proceed differently, creating energy so rapidly that stars become unstable. If it were weaker, the fusion of hydrogen into helium might not proceed efficiently. In that case, the primary energy source of stars, proton-proton fusion, would fail, leaving the universe dark and chemically inert. Even the masses of elementary particles play critical roles. The ratio of proton mass to electron mass sets the scale of atomic behavior. Alter that ratio and the way atoms interact changes. In a star, these interactions dictate how easily matter compresses, how heat is transferred, and how energy escapes from the core. Small shifts could lead to stars that cannot regulate their temperature, stars that collapse prematurely, or stars that never ignite at all. Opacity, the measure of how easily photons travel through stellar material, is another finely tuned quantity. If opacity were significantly lower, energy would escape so quickly that stars would need much hotter cores to balance gravity. If opacity were higher, energy would become trapped, causing violent convection and instability. Either extreme disrupts the steady glow that makes long-term habitability possible. When all these conditions align, stars like the Sun emerge objects that provide steady, predictable energy for immense spans of cosmic time. This stability is not incidental. It is a product of a deep and precise coordination of forces. Without stars that burn slowly enough for complex chemistry to unfold, the universe would contain matter but no means of sustaining the environments required for life. Understanding how rare this balance may be pushes us forward to another essential ingredient in the story: the formation of elements themselves. Stars are not just sources of light, they are factories forging the atoms that make planets, oceans, atmosphere, and eventually living systems. The stability of stars sets the stage, but their true significance emerges in the nuclei they forge. Every atom heavier than helium owes its existence to processes that depend on an extraordinary chain of coincidences. Without those coincidences, the periodic table would collapse into a short list of simple elements, and the universe would be devoid of the chemical diversity required for life. The most striking example of this fragility is the production of carbon and oxygen, two elements that sit at the center of biology on Earth, yet emerge only through an extremely narrow set of nuclear conditions. Inside, stars' hydrogen fuses into helium through familiar pathways. But helium cannot simply combine in pairs to form stable nuclei. The next steps in the sequence involve rare interactions, the most important of which is the triple alpha process. In this reaction, 3 helium nuclei collide and momentarily form a configuration that becomes carbon. This moment exists only because of a precise nuclear resonance, a point where the energies of the interacting particles align almost perfectly. If this resonance were shifted by even a few percent, carbon production would drop dramatically. Without carbon, the scaffolding for complex chemistry disappears. Molecules cannot chain together, structures cannot encode information, life becomes impossible. Yet the fragility does not end there. The same process that forms carbon also threatens to destroy it. If the resonance that aids carbon formation was slightly higher, the reaction would proceed too efficiently, converting nearly all carbon into oxygen. In that case, the universe would contain abundant oxygen but almost no carbon. If it was slightly lower, oxygen would be underproduced, leaving stars with an excess of carbon and too little oxygen to form water rocks and stable planetary environments. The balance between these two elements depends on a narrow overlap in nuclear energy levels, an overlap that appears almost perfectly positioned to permit both to coexist in significant amounts. Supernovae add another layer of constraint. These explosions are responsible for scattering heavy elements across the galaxy, seeding future generations of stars and planets. The violence of a supernova depends on the interplay between gravity and nuclear degeneracy pressure. If the forces governing these interactions were altered even modestly, the explosions might fail to eject heavy elements, trapping them deep within stellar remnants. A universe with few supernovae would struggle to enrich its interstellar medium. Without enrichment, planets would lack the metals needed for magnetic fields, geological activity, and atmospheric retention features that are essential for long-term habitability. Neutron capture processes, which create many of the elements beyond iron, also rely on precise timing and energy conditions. Too much neutron flux and nuclei become unstable. Too little and heavier elements fail to form. The resulting abundance pattern, the distribution of elements that fill the periodic table, is not an accident. It emerges from a narrow interplay between nuclear cross-sections, stellar lifetimes, and energy release mechanisms. These requirements point to a deeper lesson. Chemistry is not inevitable. The diversity of matter we rely on demands a specific sequence of events that depend on fine balances inside stars. Carbon, oxygen, nitrogen, phosphorus, silicon, iron, none are guaranteed outcomes of nuclear physics. Their existence reflects a coordination of nuclear forces that seems finely arranged to support complex structures. Once these elements accumulate in interstellar clouds, they set the stage for the next chapter of the story, the formation of planets capable of nurturing stable environments. But just like carbon and oxygen, planets owe their existence to an equally delicate arrangement of physical conditions, one that determines whether solid worlds can form at all. and whether they can last long enough for life to emerge. Once the universe contains a meaningful supply of heavy elements, the next question becomes whether these materials can organize into solid worlds. Planet formation seems straightforward from a distance. The gradual gathering of dust, the collision of rocks, the sculpting of orbits. But the underlying physics that allows this sequence to unfold is astonishingly sensitive. Change the laws by even modest amounts and the path from stardust to a stable planet collapses. The story begins inside protoplanetary disks, thin structures of gas and dust orbiting young stars. Dust grains collide, stick, and gradually grow larger, but their ability to stick depends heavily on the electromagnetic force and on the precise behavior of molecular bonds. If the fine structure constant were shifted enough to alter bonding strengths, dust grains would fail to cohere. The disk would remain a diffuse cloud instead of collapsing into solid bodies. Without adhesion at the microscopic level, no rocky planets could emerge. Gravity then takes over, but only after particles grow large enough for their own mass to matter. The strength of gravity determines how quickly larger bodies can form and how stable they remain as they accrete surrounding material. If gravity were weaker, the disk would dissipate before planet formation could begin. If stronger collisions would become destructive rather than constructive, pulverizing early planetesimals instead of allowing them to merge. The process requires a balance where impacts are energetic enough to reshape evolving worlds, but gentle enough not to erase progress. The distribution of heavy elements further constrains the outcome. Planetary cores depend on iron and nickel produced in previous generations of stars. If the strong nuclear force or neutron capture rates had been different, iron might not have occupied a stable position in the periodic table. Without iron's unique combination of density and magnetic properties, planets could lack molten cores and global magnetic fields. A world without magnetic shielding faces relentless radiation from its star-stripping atmospheres and sterilizing surfaces. Atmospheric stability also relies on finely tuned constants. Molecules like nitrogen, carbon dioxide, and water must exist in temperature and pressure ranges compatible with long-term climate regulation. The boundaries between solid, liquid, and gas phases depend on the mass of the electron, the charge of the proton, and the interplay between molecular bonds and thermal energy. Altering these constants shifts phase boundaries dramatically. A world like Earth might instead be locked in permanent ice, smothered in superheated vapor, or unable to hold any atmosphere at all. Even orbital architecture is not guaranteed. The gravitational interactions between planets must avoid resonances that destabilize orbits. In universes where gravity or particle masses differ slightly, planetary spacing changes, orbital periods drift, and long-term stability becomes unlikely. Worlds may plunge into their stars, be ejected into interstellar space, or collide with their neighbours before life has a chance to begin. Radiogenic heating introduces another subtle requirement. The decay of heavy isotopes like uranium and thorium supplies internal heat that drives plate tectonics and volcanism. These processes recycle nutrients, regulate carbon dioxide, and maintain climatic stability. But radiogenic heating depends on nuclear half-lives, which arise from precise relationships between fundamental forces. A shift in those relationships would alter heat flow inside planets, either freezing geological activity or causing catastrophic instability. Taken together, these constraints show that rocky planets with long-term habitability are not trivial products of cosmic evolution. They are outcomes of a finely balanced interplay among nuclear physics, chemistry, gravity, and thermodynamics. Each piece must fall into place for a world to become more than a sterile rock drifting through space. And yet, even when planets form successfully, their environments must remain stable for extraordinary periods of time. This leads us to the next question. What conditions allow planets to maintain temperatures, radiation levels, and chemical cycles compatible with the slow development of life? Even if a planet forms under the right conditions, that achievement is only the beginning. Life requires not just a place to exist, but an environment that remains within workable limits for immense spans of time. Temperature, radiation, atmospheric chemistry, and orbital dynamics must all fall into regimes where complexity can emerge and persist. The universe offers these windows only sparingly, and their existence depends on an intricate chain of physical relationships that must hold steady across billions of years. Temperature is one of the most unforgiving requirements. Chemical reactions proceed only within certain thermal boundaries, and the liquid phase of water, the medium most conducive to complex chemistry in our universe, occupies an extremely narrow range. That range depends on numerous constants: the mass of the electron, the charge of the proton, the ratio of specific heats, and the balance of molecular interactions. Change these constants and water's phases shift dramatically. Its boiling point might fall so low that oceans evaporate under modest sunlight, or rise so high that liquid water becomes rare even in cool environments. A planet's temperature becomes less a controllable property, and more an unstable outcome of altered physics. But temperature alone does not define habitability. Radiation plays an equally decisive role. Stars emit a spectrum of high-energy particles and photons, many of which can disrupt or destroy delicate molecular structures. Life on Earth depends heavily on the sun's stability, a quiet star compared with the more violent types that dominate many regions of the galaxy. If electromagnetic coupling was slightly stronger, stellar flares would release far more energetic bursts, overwhelming magnetic fields and stripping away atmospheres. If weaker fusion within stars would produce different radiation distributions, possibly pushing ultraviolet and X-ray emissions into ranges that either sterilize surfaces or fail to provide the energy needed for chemical reactions that lead to life. Magnetic fields help moderate these dangers, but their existence is itself a fine-tuned outcome. A planet needs a molten core, proper rotation rate, and specific heat flow to sustain a dynamo. Without these, stellar winds gradually erode atmospheres, leaving surfaces barren. Yet the factors governing dynamo stability, core composition, isotopic heat sources, viscosity of mantle materials depend ultimately on nuclear and particle physics. Even slight deviations in elemental abundances or decay rates can disrupt the delicate circulation patterns inside a planet. Atmospheric stability introduces another constraint. Greenhouse gases regulate a planet's climate by trapping heat, but their behavior depends on molecular vibrational modes that are highly sensitive to physical constants. Adjust these constants and the infrared absorption spectrum shifts, either trapping too much heat or too little. A world might flip between runaway greenhouse conditions and global glaciation, unable to maintain the steady temperatures that evolution requires. Orbit and rotation complete the picture. A planet must maintain a stable path around its star without entering resonances that amplify eccentricities. Tidal forces must be strong enough to stabilize rotation, but not so strong that they lock the planet too early or generate catastrophic heating. Even small changes in gravitational strength or planetary mass ratios alter these dynamics. In many hypothetical universes, stable long-term orbits may be exceedingly rare. Taken together, these requirements reveal that habitability is not a single condition, but a convergence of multiple, finely tuned factors. A universe must permit stable stars, favorable chemical pathways, solid planets, and consistent environmental conditions before life can arise at all. Each step depends on the last, forming a chain that stretches from the quantum scale to galactic architecture. The fragility of these conditions raises an obvious question. What happens in universes where even one parameter fails to land in the correct range? To explore this, we need to imagine how alternate universes unfold when their constants deviate from ours. Exploring alternate universes is not an exercise in fantasy. It is a way of understanding why our own universe works at all. When we adjust a single constant gravity, electromagnetism, nuclear strength particle masses, we reveal just how narrow the viable region for complexity truly is. These thought experiments do not describe parallel worlds we can travel to. Instead, they expose the structural dependencies hidden within the physics we take for granted. Imagine a universe where gravity is only slightly stronger. Gas clouds collapse more quickly, forming stars that burn hotter, brighter, and far more briefly. Most stars live for only a few million years, far too short a window for planets to cool, oceans to form, or chemistry to grow in complexity. Solar systems in such a universe would be chaotic, dominated by radiation, and stellar winds with little opportunity for long-term stability. Even if planets formed, they would experience constant gravitational disturbances from rapidly evolving stars, shift gravity in the opposite direction, and another problem emerges. Gas clouds struggle to collapse at all. The universe fills with diffuse dim stars or objects so cool that fusion barely proceeds. Heavy elements become exceedingly rare because the fusion chains required to create them cannot operate efficiently. Without carbon, oxygen, silicon and iron, the building blocks of planets and life never appear. Worlds might exist as cold hydrogen spheres drifting quietly through darkened space, incapable of supporting complex chemistry. The electromagnetic force shapes another set of outcomes. If electromagnetic coupling were stronger, electrons would bind more tightly to nuclei, shrinking atoms and making chemical reactions slow or impossible. Temperature thresholds for molecular stability shift dramatically. Organic chemistry, already a delicate arrangement of bonds and energies, would collapse under the new constraints. Life, at least in anything resembling its terrestrial form, becomes unworkable. A weaker electromagnetic force leads to atoms that barely hold together. Molecules drift apart under thermal motion. Complex structures fall apart before they can accumulate meaningful information. In such a universe, chemistry behaves less like a toolbox for building life and more like a random scattering of unstable interactions. The strong nuclear force introduces even more dramatic alternatives. Increase its strength, and nearly every proton merges into heavier nuclei erasing hydrogen almost entirely. Without hydrogen, stars cannot ignite through the proton-proton chain, and water, an essential solvent in our universe, cannot form. Decrease the strong force and nuclei fail to bind. The periodic table collapses to 2 or 3 elements. Stars cannot synthesize carbon or oxygen, and the universe becomes a barren expanse of lightweight atoms drifting forever. Particle masses produce similarly restrictive outcomes. A heavier electron shifts atomic energy levels, altering every form of chemistry. A lighter electron weakens the stability of complex molecules. Changes to the masses of quarks reshape the structure of protons and neutrons, sometimes preventing them from forming at all. A universe without stable protons is not a universe of altered life. It is a universe without matter. Even the cosmological constant, a parameter that governs the acceleration of cosmic expansion, sits within a minuscule range that permits galaxies to form. Increase it slightly and space expands too rapidly for matter to gather. Decrease it and the universe collapses before stars can shine. This constant is one of the most finely tuned quantities known to science, and its value remains one of the deepest puzzles in cosmology. These scenarios reveal a consistent pattern. Most universes that differ from ours in even minor ways fail to produce long-term structure. They do not evolve stars, planets, or chemistry. They remain eternally simple. Only a narrow slice of parameter space leads to complexity, and within that slice sits the universe we inhabit. This raises a profound question. If so many sets of physical laws produce sterile outcomes, why does our universe fall into the rare range that supports structure and life? One possible answer emerges when we consider a larger context, one in which our universe is not unique but part of a vast multiverse. If so many possible universes collapse into disorder, the moment a constant shifts, the natural response is to ask why our universe escaped that fate. One hypothesis shifts the burden from a single cosmic lottery to a vast landscape of possibilities. The multiverse. In this view, our universe is not the only one, and the laws we observe are not universal mandates but local conditions, settings, that vary across different cosmic regions or branches of reality. Several scientific frameworks point toward this possibility. Eternal inflation, one of the leading ideas in modern cosmology, suggests that space did not stop expanding uniformly after the Big Bang. Instead, different regions may have undergone separate inflationary phases, each cooling into a universe with its own physical constants. Tiny fluctuations in energy density could determine the properties of each region, creating an enormous variety of outcomes across an ever-growing multiverse. Some regions would possess laws too unstable for structure. Others might allow stars and galaxies to form. A small fraction might permit life. String theory offers another route. Its equations describe a vast landscape of possible vacuum states, each corresponding to a different set of physical constants. These states are not slight variations on a theme, they represent entirely distinct versions of physics. If the universe can occupy many of these states, then the values we observe are simply one selection from a far larger menu. The sheer number of possibilities, potentially on the order of 10 to the 500, suggests that fine-tuning may not require a special explanation. In a landscape so large, some universes will inevitably fall into the narrow range compatible with complexity. Quantum mechanics adds a further layer of interpretation. In some formulations, such as the many worlds interpretation, every quantum event leads to branching outcomes, each creating a distinct version of reality. These branches share a common origin but diverge endlessly. While these universes typically share the same physical laws, the concept reinforces the idea that reality may be far larger and more varied than what we observe. The multiverse hypothesis does not claim that all universes support life. In fact, most would not. Nearly all configurations of physical constants lead to immediate collapse, runaway expansion, or universes filled only with diffuse particles lacking structure. But if the multiverse contains enough diversity, then the existence of at least one life-permitting universe ceases to be remarkable. We simply inhabit a region where the conditions allow observers to arise. This does not explain why a multiverse exists in the first place, but it reframes fine-tuning as a natural consequence of sampling from an enormous set of possibilities. Critics point out that we cannot test the multiverse directly. By definition, other universes may lie beyond our causal reach. Yet indirect evidence remains possible. If patterns in the cosmic microwave background or subtle imprints in large-scale structure reveal hints of collisions with other bubble universes, the hypothesis gains credibility. Even without direct observation, the multiverse emerges as a plausible solution to the fine-tuning problem, because it replaces a single improbable event with a statistical distribution of outcomes. Under this framework, fine-tuning becomes less like an engineered feature and more like a selection effect. Out of a vast ensemble of cosmic possibilities, we find ourselves in one of the rare universes where matter organizes into atoms, atoms into stars, stars into planets, and planets into conditions stable enough for life. But this reasoning only shifts the question. If our universe is one among many, what determines the distribution of laws across the multiverse? And why does the multiverse exist at all? To approach those deeper questions, we must confront the concept at the heart of fine-tuning, the role of the observer in shaping what can be known about the universe. A universe capable of producing observers is necessarily unusual. That idea lies at the core of anthropic reasoning, a concept that often feels philosophical, but emerges directly from physics. When we examine the fine-tuning of the constants, the early expansion rate, and the narrow pathways that lead from simple particles to complex chemistry, it becomes clear that most hypothetical universes would not support anything capable of asking questions. This alone shapes what we can observe. Anthropic reasoning does not claim that the universe is designed for life. Instead, it acknowledges a simpler truth. Observers can arise only in universes where the conditions allow them to exist. If countless universes exist across a multiverse, most of them will not contain observers. Those universes remain forever unmeasured because there is nothing within them capable of making measurements. Our perspective then is inherently biased. We cannot witness sterile universes, only the rare ones where conditions fall inside the narrow life-permitting range. The logic resembles a selection filter. Even if universes with favourable constants are exceedingly rare, the probability of finding oneself in one of those rare universes rises to 100%. Once the presence of observers is taken into account, a universe that collapses in the first second or expands too quickly for structure to form never produces the biological or non-biological intelligence required to contemplate its own parameters. Only universes with the right values host beings who wonder why those values exist. This reasoning becomes especially relevant when we examine constants like the cosmological constant. Its measured value is unimaginably small, far smaller than naive quantum field predictions. Increase it even modestly and galaxies fail to form. Decrease it and the universe collapses prematurely. The existence of observers forces the value into a razor-thin band not because the constant must take that value universally, but because observers cannot exist in regions where the constant takes other values. In that sense, observation itself becomes a constraint. Yet anthropic reasoning is not a complete explanation. It clarifies why we should not be surprised to find ourselves in a life-friendly universe, but it does not explain why such universes are possible in the first place. It describes observational bias, not the fundamental origin of the laws. Still, the anthropic principle provides a consistent framework for interpreting fine-tuning without invoking improbable coincidences or untestable assumptions about purpose. It shifts the question from why does the universe allow life to why are these the conditions under which observers can arise. This shift has profound consequences. It reframes our understanding of life as a natural outcome wherever physics permits a long-lived environment for complexity. It also implies that life reveals only a small fraction of what reality may contain. Most possible universes remain forever silent not because they lack structure, but because they do not allow structures that question themselves. But if anthropic reasoning can explain why we observe a life-friendly universe, it cannot answer the deeper puzzle behind all fine-tuning. What determines the laws of physics in the first place? To move forward, we must examine whether the laws themselves, and not just their values, might arise from deeper principles, symmetries, vacuum states, or emergent structures that sit beneath the surface of what we call reality. The recognition that our universe permits observers naturally leads to a more difficult question. Why do the laws of physics exist in the specific form we observe at all? Fine-tuning becomes even more striking when we realize that the constants are only part of the story. Beneath them lie the rules that govern how particles behave, how forces emerge, and how space-time responds to energy. These rules do not explain themselves. They simply are. And yet every structure in the cosmos depends on their stability and coherence. Modern physics identifies symmetry as one of the deepest organizing principles. Many laws, conservation of energy, momentum, and electric charge arise directly from symmetries in the mathematical structure of physical theories. If time translation symmetry holds, energy remains conserved. If space is uniform, momentum obeys predictable rules. These relationships are not optional. Without them, systems would behave erratically. Planets would not follow stable orbits. Chemical reactions would not proceed reliably. Evolution in any form would have no foundation. The fact that symmetries exist at all is one of the profound features of our universe. But symmetries do not fully determine the specific values of constants or the range of forces. They describe structure rather than content. To address the origin of the laws themselves, we sometimes turn to the concept of symmetry breaking. At extremely high energies, conditions present in the first instance after the Big Bang, the forces we see today may have been unified. As the universe expanded and cooled, that unified structure fractured, giving rise to separate interactions with different strengths. The masses of particles may have emerged from the configuration of fields that settled after this break. Yet this explanation only shifts the question one step earlier. Why did symmetry break in that particular way and not another? Another perspective considers the vacuum state of the universe. In quantum field theory, what we call empty space is actually a complex environment defined by the values of underlying fields. These fields can settle into many possible configurations, each corresponding to a different set of physical laws. The vacuum we inhabit is just one option among many. Why this one? Why a vacuum that permits atoms, chemistry, stars, and life? The equations allow countless alternatives where matter cannot stabilize or forces tear structures apart before they form. Some researchers propose that the laws we see might be emergent rather than fundamental. Just as temperature and pressure emerge from countless microscopic interactions, the laws of physics may arise from deeper layers of reality not yet described by known theories. In this view, particles and forces are not the ultimate building blocks, but effective descriptions of more primitive entities. If that is true, fine-tuning might reflect the properties of these deeper layers, rather than arbitrary numerical coincidences. But what those layers are and how they generate the laws we observe remains an open question. Even space-time itself may not be fundamental. Certain theories suggest that geometry emerges from patterns of quantum entanglement. If entanglement patterns shift the resulting space-time and therefore the laws that govern it could differ drastically. This approach hints that our universe's laws arise from informational structures rather than intrinsic physical properties. But again, we face the same mystery. Why these structures and not others? When we follow the chain of explanation downward from planets to atoms, from atoms to particles, from particles to symmetries, and from symmetries to vacuum states, we eventually reach a boundary. Beyond that boundary, physics no longer provides answers. The origin of the laws remains unexplained and perhaps unexplainable using current frameworks. This recognition does not diminish our understanding of the universe. It highlights how much more remains concealed beneath the surface of what we know. Yet the mystery has a practical implication. Whatever determined the laws of nature produced a universe capable of generating complexity. And that leads back to the final step in our journey. What this extraordinary alignment reveals about life, about the cosmos, and about our place within the rare environments where complexity can arise at all. Reaching the foundation of the laws leaves us with a universe that appears both astonishingly precise and fundamentally mysterious. Every step in the chain, from the emergence of stable nuclei to the formation of stars, planets, and long-lived environments, relies on parameters that fall within narrow, life-permitting ranges. The deeper we dig, the clearer it becomes that complexity is not the natural state of most conceivable universes. It is a rare outcome that emerges only when the architecture of physical law aligns in just the right way. This perspective does not imply purpose. It does not claim intention or design. It simply acknowledges the improbability of the arrangement that surrounds us, the elements that build planets, the reactions that power stars, the chemistry that encodes information, and the stability that allows evolution to proceed, all depend on relationships between constants that could have taken countless other forms. And yet against these odds, our universe supports structures able to reflect on their own origins. Understanding fine-tuning alters how we see life. Instead of treating biology as an inevitable outcome of physics, we recognize it as a secondary phenomenon built upon deeper layers of structure that must first cooperate. Life becomes a tracer of the universe's rare, permissive pockets, regions where matter, energy, and time all fall into regimes that allow information to grow. In this way, life reveals something about the underlying framework of the cosmos. Where life exists, the laws must have taken values that enable stability. Where the laws differ, complexity never gets the chance to begin. Yet this realization also expands the scope of what might be possible. If the multiverse contains many universes, each with different laws, then life could take forms we cannot predict arising wherever the local rules permit patterns to persist and adapt. The fine-tuning of our own universe becomes one example among many, not a unique miracle, but a window into a broader landscape of cosmic variation. Somewhere in that landscape, other forms of complexity might emerge under rules unfamiliar to us, writing their own histories in environments we would not recognize. Standing at the end of this journey, the fine-tuned nature of our universe does not provide a final answer. Instead, it reframes the question. The existence of life becomes not just a biological fact, but a clue pointing toward the deeper workings of reality. It suggests that the laws of nature, whatever their ultimate origin, contain within them the capacity to generate observers, beings who can examine the universe and identify the narrow pathways that make their existence possible. In the end, the mystery remains open. We do not yet know why the laws are the way they are or whether they could have been different, but by tracing their consequences across cosmic history, we uncover a striking truth. Our ability to wonder about the universe is itself a product of those laws. Every atom in every living organism, every spark of awareness, every thought about our origins all arise from a precise balance struck in the first moments of time. The universe does not offer explanations freely, but it does reveal patterns, and in those patterns we find the outline of a story still unfolding. A story that began with tuned constants and expanding space, and may yet lead us toward a deeper understanding of why anything exists in a form capable of asking questions at all. If fine-tuning reveals how narrow the path to complexity truly is, then another question naturally rises behind it, one we have not yet explored. Even in a universe where the laws are aligned, where stars burn steadily, and planets form from enriched clouds of dust, the emergence of life is still not guaranteed. Conditions may be stable, but stability alone does not create biology. Between a habitable world and a living one lies a deeper threshold, the transformation of lifeless chemistry into systems that store information, adapt, and evolve. That transition remains one of the most obscure steps in cosmic history. We know that the early Earth provided the right environment. We know that chemistry assembled the necessary molecules, but the precise moment when non-living matter crossed the boundary into self-replicating order remains hidden. And beyond that, mystery lies an even larger one. Is this transition a rare accident or a universal process that should unfold wherever conditions permit? Our exploration now shifts from the structure of the universe to the structure of life itself, from the laws that make complexity possible to the mechanisms that transform potential into biology. For billions of years after the universe began, space was filled with light gas, dust, and drifting worlds. Stars formed, burned steadily, and enriched their surroundings with new elements. Planets cooled beneath young skies, oceans gathered, storms moved across empty continents, and the chemistry of each world settled into patterns defined by its own history. Yet across all this structure, the universe remained silent. There were atoms and molecules, cycles of heat and motion, but nothing that could sense, respond, or remember. The transition from silence to life is one of the rarest steps in cosmic evolution, and also the most obscure. We know that chemistry is capable of incredible complexity. We know that planets provide energy, minerals, and stable environments, but somewhere between simple reactions and systems that copy information, a threshold is crossed, a moment when matter begins to organize itself in a way that persists, adapts, and evolves. Life does not emerge simply because the universe allows it. The laws of physics may set the stage, but the spark that transforms lifeless chemistry into living systems requires an intricate choreography. Molecules must not only form, they must interact in networks that favor structure over randomness. They must store patterns that can survive from moment to moment. And eventually they must learn through replication and variation how to refine those patterns across time. This journey begins long before biology takes shape. It begins when a planet cools enough for water to collect, when energy flows through its surface in cycles, and when chemistry becomes rich enough for unexpected arrangements to appear. Somewhere in those early reactions lies the first step toward life, a system that can hold on to information long enough for evolution to begin. Understanding that transition is not simply a matter of chemistry or geology. It is an exploration of how the universe moves from potential to possibility, from a world filled with building blocks to a world that can build itself. The mystery deepens when we consider how little the universe contributes once a planet cools. Physics establishes the rules, but it does not dictate the pathways. The laws allow complexity, yet leave chemistry to explore an immense landscape of possibilities, most of which never lead to anything stable. A planet may host oceans, minerals, sunlight, and the full inventory of life's potential ingredients. But without a mechanism that concentrates reactions, favors useful patterns, and filters out noise, the world remains a chemical ocean drifting without direction. What makes this transition so remarkable is the scale of the challenge. Molecules form and break apart constantly. Bonds assemble and dissolve in endless cycles driven by temperature, pH, radiation, and turbulence. Information cannot persist in this environment unless the chemistry finds a way to protect it. And before that can happen, the chemistry must learn to create patterns in the first place. Patterns that are more than chance arrangements of atoms, patterns that begin to influence what happens next. The early Earth offered such conditions, but even then the path was uncertain. Its atmosphere was thick with volcanic gases, its oceans were loaded with dissolved metals, the surface faced relentless UV radiation from a young sun. These conditions were not gentle, but they were active. Energy flowed through the environment in continuous pulses, creating endless opportunities for molecules to interact in new ways. The planet became a natural laboratory, one where every wave, every lightning strike, every vent of mineral-rich water represented another experiment. In this chaotic setting, chemistry did what chemistry always does. It explored. It filled the oceans with millions of variations, each fleeting, each vulnerable to disruption. Yet among this swirling complexity, certain reactions began to stand out. Some combinations of atoms formed structures that lasted longer than others. Some arrangements became more likely to reappear. These small biases, almost invisible at first, marked the earliest hints of directionality. Tiny steps towards systems that could carry information forward. That directionality matters. Life is not defined by the molecules it contains, but by the persistence of patterns over time. A molecule that can influence its own formation is different from one that appears by chance. A network of reactions that stabilizes itself becomes something more than chemistry. It becomes a precursor to evolution. These networks do not need to resemble modern biology. They only need to survive long enough for refinement to begin. The universe provides countless planets where chemistry can unfold, but only a few where such networks can persist. Temperature must sit in the right range. Water must remain stable. Energy must arrive in balanced doses, not so intense that it destroys everything, not so weak that reactions stagnate. Most worlds remain silent because these conditions never align for long enough. Yet on Earth, and potentially on other planets across the galaxy, the environment sustained the narrow window where chemistry could test idea after idea until a few gained traction. Understanding this window is the first step toward understanding life's origin. It is not a single moment, not a sudden spark, but a gradual shift. Chemistry, becoming capable of memory, capable of selection, capable of exploring its own possibilities. Once that shift begins, the path toward life becomes increasingly accessible. But before we can follow that path, we must examine the world where it happened, a young Earth poised on the edge of transformation. The early Earth was not a calm world waiting patiently for life to appear. It was a dynamic, unstable planet still reshaping itself after its violent formation. Its surface glowed with residual heat. Oceans simmered under a sky dense with volcanic gases. Meteorites continued to fall, delivering both destruction and new chemistry. Across this landscape, reactions unfolded under conditions that would seem hostile today, but proved essential for the first steps toward biology. The atmosphere was dramatically different from the one that sustains modern ecosystems. It lacked free oxygen and was instead dominated by carbon dioxide, nitrogen, methane, water vapor, and sulfur compounds. These gases absorbed sunlight differently, altering surface temperatures and creating a climate far more dynamic than anything we experience now. Lightning flashed frequently through thick clouds, injecting bursts of energy directly into the chemical inventory of the young oceans. Ultraviolet radiation from the sun reached the ground in intensities that would be dangerous for modern organisms. Yet this radiation was one of the most effective drivers for forming the complex molecules that later became crucial to early life. The oceans themselves were not uniform pools of water. They contained gradients, temperature gradients near volcanic vents, salinity gradients in tidal regions, chemical gradients where river runoff mixed with seawater. Each gradient represented an opportunity. Reactions behaved differently depending on their environment, and early Earth offered thousands of distinct microenvironments where chemistry could explore various pathways. Mineral surfaces played a powerful role in this process. Clays, basalts, and metal sulfides provided catalytic sites that concentrated molecules and guided reactions that would proceed inefficiently in open water. Tidal cycles, driven by a closer moon and faster rotation of the planet, created repeated wet-dry rhythms along shorelines. These cycles may have been especially important. When water evaporates in shallow pools, molecules become concentrated, enabling bonds that are rare in dilute conditions. When water returns, these new structures disperse and interact with a wider chemical environment. Each cycle represents an iteration, an opportunity for complexity to increase, for new reactions to appear. and for fragile molecular patterns to persist a little longer than before. Geological activity added further complexity. Earth's crust was young, thin, and mobile. Heat from the interior drove constant resurfacing through volcanic eruptions and hydrothermal circulation. At ocean ridges, mineral-rich fluids emerged from deep within the crust, carrying iron, sulfur, and trace metals that catalyzed critical reactions. These vents created warm, chemically rich oases on an otherwise unstable planet. In such environments, energy was not provided by sunlight but by steep chemical gradients, natural batteries capable of driving reactions efficiently and continuously. Magnetic shielding also played a subtle but crucial role. Despite its chaotic surface, the young Earth already possessed a magnetic field generated by movement in its molten core. This field protected the planet from the most harmful charged particles streaming from the Sun. Without that protection, the atmosphere might have been stripped away, removing the medium in which early chemistry operated. Instead, the magnetic field preserved an envelope where water could remain liquid, and environments could remain stable long enough for complex reaction networks to arise. These conditions did not guarantee life, but they created a setting where the improbable became possible. The young Earth was a planet full of energy sources, chemical diversity, and environmental cycles, all essential ingredients for pushing chemistry toward greater structure. What matters is not that these conditions were perfect, but that they created a world capable of continuous experimentation. Out of trillions of reactions unfolding every second, a few began moving in directions that could eventually lead to information replication and selection. But before life could emerge, the raw ingredients had to form the molecules that would become the scaffolding for biology. Understanding their origins takes us deeper into the chemistry of the early planet, and into the broader cosmic story that provided Earth with the atoms capable of building life. Long before the first protocell took shape, the universe had already prepared the ingredients that early Earth would later assemble into living systems. The atoms essential for biology, carbon, hydrogen, nitrogen, oxygen, sulfur, and phosphorus, did not originate on the planet itself. They were forged in stars that lived and died billions of years earlier. Supernova scattered these atoms across interstellar space, where they mixed with cold molecular clouds. From those clouds, new stars and planets formed, including the Sun and Earth. By the time our planet cooled, it inherited a complex chemical legacy shaped by events that unfolded long before its existence. Among these elements, carbon occupies a unique position. Its exceptional bonding versatility makes it unlike any other atom in the periodic table. Carbon can form long chains, branching structures, rings and stable frameworks capable of supporting enormous molecular complexity. Its bonds are strong enough to maintain structural integrity, but not so rigid that they restrict chemical diversity. Silicon, often imagined as an alternative, cannot match carbon's flexibility. Its bonds are heavier, less stable in water, and confined to more limited geometries. In nearly every plausible chemical environment, carbon outperforms other elements when building intricate molecules. It is not an accident that life on Earth is carbon-based. Carbon provides the only known scaffolding that can sustain dynamic information-rich chemistry. Water, too, is far more than a passive solvent. Its polar nature allows it to dissolve a wide range of compounds, enabling molecules to move, collide, and react. Its hydrogen bonding behavior organizes molecules in subtle ways that stabilize certain structures and destabilize others. Water's density, curve heat capacity, and ability to remain liquid over a broad temperature range create a remarkably stable environment for chemistry. In the oceans of the early Earth, water facilitated the assembly of amino acids, sugars, lipids, and other building blocks. It allowed reactions to occur predictably, while also dispersing products into new environments where further reactions could take place. Yet the building blocks of life did not arise solely from Earth's internal chemistry. Meteorites delivered amino acids, simple sugars, and organic compounds formed in interstellar conditions. These molecules survived their descent through the atmosphere and accumulated in oceans and tidal pools. Their presence indicates that the universe naturally produces many of the precursors to biology. The steps that follow, however, require specific environments, places where these molecules can be concentrated, stabilized, and pushed into more elaborate reactions. Once on Earth, these organic molecules interacted with minerals that acted as catalysts. Metal sulfides, clays, and iron-rich surfaces guided chemical transformations that would occur too slowly or inefficiently in open solution. These minerals stabilized fragile molecular intermediates, helped form longer chains, and even provided surfaces where carbon-based molecules could align and react with higher probability. This interaction between organic matter and geological substrates was crucial. Without it, the complexity required for life would be exceedingly difficult to achieve. Carbon-based molecules began to link into longer chains, peptides, early nucleic acid-like strands, and lipid precursors. Each new category of molecule introduced new capabilities. Peptides offered structural stability and catalytic potential. Lipids created compartments that defined interior and exterior environments. Nucleotide-like molecules carried patterns that could, under certain conditions, replicate. None of these molecules were alive, but together they formed a growing toolkit, a chemical inventory from which life could eventually emerge. The early Earth thus became a convergence point. Cosmic ingredients delivered by ancient stars' water-driven chemistry, unfolding across oceans and shorelines and mineral surfaces, shaping reactions with remarkable precision. This interplay set the stage for the next transformation, the moment when energy began to push these molecules into increasingly organized structures, providing the directional force that turned potential into active chemistry. Life's earliest chemistry did not emerge in stillness. It required energy, steady, abundant, and delivered through channels capable of driving reactions far beyond what would happen spontaneously. Energy is not merely a trigger. It defines which molecular patterns survive and which collapse. Without constant input, early chemistry would drift toward equilibrium, a state with no gradients, no direction, no capacity for complexity. The young Earth escaped this stagnation through a remarkable diversity of energy sources, each shaping prebiotic chemistry in different ways. Lightning was among the most dramatic contributors. The dense, warm atmosphere of the early planet produced thunderstorms far more intense than those seen today. Each bolt delivered millions of joules of energy in a fraction of a second, splitting atmospheric molecules and recombining them into new forms. In such conditions, simple gases like methane, nitrogen, and water vapor could transform into amino acids and other organics, an effect famously demonstrated by the Miller-Urey experiment. Although that experiment captured only a fraction of the true atmospheric complexity, it proved that lightning served as a potent engine for generating life's molecular scaffolding. Ultraviolet radiation from the young sun provided a more continuous and widespread energy source. Modern organisms treat UV light as dangerous because it breaks chemical bonds, damaging DNA and proteins. But before life existed, this same destructive capability became a powerful creative force. UV radiation drove reactions that otherwise would not occur at low temperatures, enabling the formation of nucleotides and other fragile molecules that play central roles in genetic information. In shallow pools and surface waters, sunlight continually reshaped the chemical landscape, producing intermediates that accumulated toward increasingly complex structures. Deep beneath the oceans, hydrothermal systems delivered a different kind of energy, steady, mineral-rich, and highly structured. At these vents, superheated water laden with metals and sulfides mixed with cooler seawater, creating steep chemical gradients. These gradients functioned like natural batteries. Molecules drifting through vent systems experienced environments where energy flowed not from light or lightning, but from electrochemical differences between surrounding fluids and mineral surfaces. Metal sulfides, especially those containing iron and nickel, acted as catalysts that guided electrons along specific pathways, allowing carbon-based molecules to assemble in ways difficult to achieve in open water. The architecture of hydrothermal chimneys also provided microenvironments where concentration and catalysis worked together. Tiny compartments formed naturally within mineral walls, trapping molecules long enough for sequences of reactions to take place. These structures resembled primitive reactors, spaces where chemical networks could evolve without being immediately diluted into the vast ocean. Some theories propose that early metabolic cycles emerged here embedded in mineral surfaces before they ever existed inside cells. Crucially, these energy sources did not act in isolation. Lightning-enriched atmospheric chemistry, UV radiation modified surface molecules, vent systems sustained long-term reaction chains, tidal cycles exposed molecules alternately to wet phases favourable for diffusion and dry phases conducive to polymer formation. Geothermal heat influenced regional environments. Together, these forces created a constantly shifting mosaic of opportunities where chemistry could explore not just new reactions but new organisational patterns. In such an energetic world, molecules were not fixed in their roles. They formed, broke apart, recombined, and occasionally arranged themselves into structures capable of influencing further reactions. Some combinations survived longer, gained stability, or promoted their own formation. These subtle advantages, amplified over countless cycles, gradually transformed simple molecules into complex networks that began to exhibit behaviours approaching what we now recognise as the foundations of biological systems. But for chemistry to cross the boundary into something more enduring, something capable of carrying information across time, it needed a way to encode patterns. Energy alone could not achieve this. Molecules had to discover a method to store structure in a persistent, reproducible form, a crucial leap that led to the first informational polymers. As molecules became more diverse and energy continued to drive reactions through every environment on the early Earth, a new challenge emerged: persistence. Chemical reactions occur everywhere, but their products vanish as quickly as they appear unless something stabilizes them. For life to begin, chemistry had to find a way not merely to produce complexity, but to preserve it to hold on to patterns long enough for refinement to occur. This requirement marks the true beginning of information in the natural world. Information at its core is pattern that influences what comes next. A molecule capable of guiding the formation of copies of itself carries information. A network that favours certain reactions over others stores a kind of memory. Before biology, this form of memory existed only through chemical stability structures that lasted longer, simply because they were hard to break. But stability alone is not enough. Life requires patterns that can replicate, mutate, and compete. To cross this threshold, chemistry needed a class of molecules capable of both storing structure and participating in reactions that create new molecules with similar structures. This is where RNA-like polymers enter the story. The early Earth likely produced a wide range of nucleotide precursors through UV-driven synthesis and mineral catalysis. Under suitable conditions, these precursors linked into short chains, forming the first primitive informational molecules. These strands did not resemble modern RNA, but they possessed key properties. They could fold into shapes that influence nearby reactions, and in certain environments, they could assist in the formation of additional strands with related sequences. Replication in this era was far from precise. Instead of the accurate copying associated with modern genetics, early polymers produced imprecise templates. But these imperfections were essential. Variation allowed certain sequences to persist longer, form more stable structures, or accelerate their own replication indirectly. Over countless cycles of formation and degradation, selection pressures emerged favouring sequences with functional shapes, catalytic capabilities, or resilience in specific environments. The first catalytic polymers were likely simple ribozyme-like molecules. Even without cellular context, folded strands could help break or form bonds in neighbouring molecules, subtly shaping the chemical environment around them. These reactions increased the likelihood that certain sequences would be regenerated, effectively biasing the chemical landscape toward patterns that supported further complexity. A loose form of evolution had begun, one governed not by organisms or cells, but by molecules themselves. These informational molecules also interacted with minerals that provided structural advantages. Porous rocks, clays, and hydrothermal vent walls concentrated polymers within confined spaces, creating micro-reactors where strands accumulated and replicated more efficiently. Water movement through these cavities refreshed the supply of building blocks while removing degraded fragments. The environment naturally selected for sequences capable of surviving these cycles, leading to gradual improvements in stability and catalytic potential. As strands became longer, their folding patterns grew more elaborate. Some shapes protected sensitive regions from degradation. Others positioned reactive groups in ways that enhanced chemical activity. Complexity increased not through sudden leaps, but through a slow accumulation of small advantages, each one improving the survival or replication rate of the molecules involved. The early Earth provided countless opportunities for these incremental changes to take hold. Through these processes, information began to matter. Molecules that stored patterns endured longer. Molecules that assisted in their own regeneration multiplied. Networks that supported reciprocal interactions where one molecule's activity created benefits for another formed early chemical ecosystems. These ecosystems were not alive, but they possessed the essential property that life depends on: the ability to explore a landscape of possibilities through variation and selection. Still, chemistry needed one more transformation before true biological evolution could begin. These polymers drifting freely in water were vulnerable to dilution and degradation. Their interactions, though occasionally productive, lacked spatial control. To become more robust, early informational systems required compartments, boundaries that defined an interior space, concentrated useful molecules, and shielded fragile polymers from the chaotic environment outside. That next step came from an unexpected source: simple lipids that assembled spontaneously into protective structures, giving rise to protocells that would reshape the path of chemical evolution. The emergence of protocells marks one of the most consequential transitions in Earth's early chemistry. Before compartments existed, informational molecules drifted through open water, forming and degrading in cycles driven by environmental conditions. Their interactions were real, but they lacked structure. Reactions that depended on proximity were easily disrupted. Patterns that held promise for further refinement were diluted as soon as they formed. Chemistry needed a way to localize itself, to create regions where useful molecules remained close enough long enough for cumulative changes to take place. Simple lipids provided that opportunity. Fatty acids produced through geological and atmospheric processes or delivered by meteorites possess a remarkable behavior in water. They spontaneously organize into membranes. Their hydrophobic tails cluster together, avoiding water, while their hydrophilic heads face outward, stabilizing the structure. When enough lipids gather, they form spherical shells, tiny vesicles capable of enclosing pockets of water. These vesicles represent more than molecular curiosities. They are natural containers defining for the first time an interior distinct from the surrounding environment. In these microscopic enclosures, informational molecules suddenly found a new context. Instead of being scattered throughout vast oceans, strands of RNA-like polymers could become trapped inside, concentrated by simple physical processes. Protocells created a sheltered environment where molecules interacted more frequently, where beneficial reaction networks were less likely to be lost, and where selective pressures began to operate on the level of entire compartments rather than individual molecules. A protocell that happened to contain a more efficient catalyst or a more stable polymer gained a survival advantage over one that did not. Membranes were not rigid structures. Early protocells were fragile, easily disrupted by turbulence, heat, or chemical imbalances. Yet this fragility may have been beneficial. When a protocell broke apart, its contents spilled into the environment, seeding other regions with useful molecules. When membranes reassembled, they captured new combinations of polymers, creating variation at the compartment level. Protocell populations thus experienced a primitive form of inheritance and diversification. Some compartments divided naturally when they grew too large. Others absorbed stray lipids and expanded. These behaviors resemble cell-like dynamics, even though no true biology existed yet. Energy flows played a key role in shaping the internal chemistry of protocells. Membranes allowed gradients to develop differences in ion concentrations between the inside and outside. These gradients provided driving forces for reactions, much like the proton gradients used by modern cells to generate energy. Even without the complex proteins that control these gradients today, early protocells benefited from the directional flow of ions across their membranes, creating favourable conditions for certain reactions to dominate. Inside these compartments, networks of molecules competed, cooperated, and refined themselves. Catalytic strands that improved membrane stability became more common. Polymers that assisted in the replication of other molecules contributed indirectly to the survival of their protocell. Over time, interactions within compartments became more structured. Some protocells maintained internal reaction cycles longer than others. Some sustained the formation of new informational polymers at a rate that matched or exceeded their degradation. In such protocells, chemical evolution could accelerate. The environment imposed additional selective pressures. Protocells near hydrothermal vents experienced constant thermal cycling, which promoted strand separation and reformation processes essential for replication. Protocells in tidal regions underwent repeated concentration and dilution, challenging their membranes and internal chemistry. Each locale favoured different strategies, encouraging a diversity of protocell types to emerge across the planet. Though still entirely chemical, protocells were more than the sum of their parts. They represented localized systems with identities temporarily fragile but capable of preserving and propagating chemical innovations. For the first time, chemistry had boundaries, inheritance variation, and competition. These properties set the stage for the next transformation, the rise of primitive metabolism and the gradual integration of information energy, capture and structural maintenance into unified systems. Before long, protocells were no longer isolated containers of random molecules. They were evolving entities subject to environmental pressures that pushed them toward greater stability and complexity. And from these early compartments, a new frontier emerged, one where protocells began refining the chemical machinery needed to sustain themselves, marking the dawn of true evolutionary dynamics. As protocells became more common across the early Earth, they entered an environment that offered both opportunity and relentless pressure. No proteole existed in isolation. Ocean shorelines and hydrothermal environments produced vast populations of these microscopic compartments, each carrying its own mixture of lipids, catalytic strands, and reaction networks. Their survival depended not only on the molecules they contained, but on how effectively those molecules interacted under constantly changing conditions. Evolution, still chemical, not yet biological, began to unfold on a planetary scale. Inside each protocell, reactions competed for resources. Molecules that degraded quickly or interfered with useful pathways faded from the population. Those that supported replication, stabilized membranes, or improved energy capture became more prominent. Unlike free-floating molecules which faced dilution and constant disruption, protocells provided environments where favorable networks could reinforce themselves over time. A protocell with an advantageous combination of molecules stood a better chance of maintaining its internal structure through cycles of growth and division. Some protocells discovered primitive metabolic tendencies, not deliberate but emergent. Certain catalytic strands promoted sequences of reactions that harvested energy from the environment more efficiently. Others facilitated pathways that converted simple molecules into more complex ones. Over time, protocells that could sustain reaction cycles longer than the rate at which molecules degraded gained a measurable advantage. Their internal chemistry persisted through environmental fluctuations that might have destroyed less resilient compartments. Competition intensified as protocells encountered one another. In regions with plentiful nutrients, protocells could grow rapidly, absorbing lipids and expanding until they divided spontaneously. In nutrient-poor zones, protocells with inefficient internal chemistry collapsed, releasing their contents into the environment. These released molecules seeded nearby protocells, introducing new components into their internal networks. Some exchanges were harmful, destabilizing membrane integrity or disrupting existing cycles. Others introduced catalytic strands that improved reaction efficiency or replication fidelity. Horizontal transfer of chemical components far older than the genetic exchanges seen in modern microbes played a major role in shaping protocell evolution. Environmental stresses further refined protocell populations. Temperature fluctuations forced membranes to adapt, selecting for lipid compositions that remained intact under rapid changes. pH shifts challenged internal reaction networks, eliminating protocells unable to regulate their internal chemistry. Even in rudimentary ways, minerals dissolved or precipitated out of solution, altering the availability of catalytic surfaces. Under these pressures, protocells capable of maintaining robust internal conditions, again not through biological regulation, but through stable chemical patterns, persisted. Some protocells drifted into environments dominated by specific energy sources. Near hydrothermal vents, chemical gradients favoured protocells with catalytic networks that exploited electron transfers across mineral surfaces. In shallower waters, UV-driven reactions selected for strands capable of protecting themselves from degradation. Along shorelines, wet-dry cycles rewarded compartments that could retain their contents during evaporation and rehydrate without structural collapse. Each niche sculpted protocell populations differently, producing a rich diversity of forms and behaviours across the planet. As networks matured, feedback loops emerged. A catalyst that improved membrane stability allowed a protocell to survive longer, increasing the likelihood that beneficial strands would accumulate inside. A strand that enhanced the formation of nucleotides indirectly promoted its own replication. These reinforcing cycles resembled a primitive metabolism, still chemical, but increasingly organized around patterns that supported persistence and growth. The distinction between environment-driven chemistry and self-sustaining networks began to blur. The most successful protocells were those that maintained a balance between structure and flexibility. Too rigid, and the compartment could not adapt to new reactions. Too fragile, and the internal network collapsed with minor disturbances. Over many cycles of division rupture and recombination, protocells drifted toward configurations that favored stability, replication, and incremental improvement. They had not yet achieved the level of coordination seen in true cells, but the foundations were in place. This gradual refinement led to a moment when protocells began to explore more integrated ways of capturing and storing energy mechanisms that improved not only their survival but the inheritance of their internal chemistry. And from this landscape of competition, a critical transition approached. The shift from loosely connected reaction networks to more cohesive systems, where molecular roles began to specialize, setting the stage for the dawn of metabolism. Despite the countless variations unfolding in every corner of the early Earth, a pattern had begun to emerge, one in which chemistry no longer drifted aimlessly, but followed pathways that built upon themselves. Protocells, once nothing more than fragile compartments holding accidental mixtures of molecules, now acted as arenas where selection and refinement continuously shaped the reactions inside. Nothing in this stage resembled life as we know it, yet the foundations of life were unmistakably forming. With every cycle of growth and rupture, with every exchange of catalytic strands and lipids, protocell populations explored a vast landscape of chemical possibilities. Some combinations destabilized their compartments, ending their line immediately. Others created fleeting advantages, making certain protocells slightly more resilient, slightly more capable of maintaining internal order. Over immense stretches of time, these incremental improvements accumulated. The chemistry within some protocells became less dependent on external chance, and more driven by the internal networks that had begun to sustain themselves. This is the moment where our understanding ends, not because the story concludes, but because the details disappear behind a curtain of deep time. We do not know which protocell first discovered a more stable way to store information, or which combination of molecules gave rise to systems that resembled primitive metabolism. Somewhere on the young planet, however, a lineage crossed a threshold. Its chemistry became coordinated enough, persistent enough, and adaptive enough to move beyond the realm of chance. That lineage would eventually lead to true cells, to genetic inheritance, and to biological evolution. But those later developments belong to another chapter. For now, all we can say with confidence is that life began not with a single spark, but with millions of chemical experiments unfolding simultaneously across a restless world. The universe prepared the ingredients. Energy shaped the reactions. Time allowed patterns to deepen. And from this interplay, Earth transitioned from a silent planet to one capable of producing systems that could sense, respond, and eventually understand. As we step away from this story, what remains is not a definitive sequence of events, but an emerging principle. Wherever the right chemistry, energy, and environment-aligned matter may find ways to preserve information, refine itself, and adapt. The cosmos is vast, and the processes that unfolded here may be neither unique nor rare. If life can emerge from nothing more than atoms and energy on one world, then countless other planets may be following their own chemical trajectories at this very moment. The search for life beyond Earth, then, is not just a search for biology. It is a search for the conditions that nudge chemistry towards structure for the worlds where patterns persist long enough to cross the boundary from reaction to evolution. Somewhere in the galaxy, in environments we have yet to witness, protocells may be forming, dissolving and reforming, quietly rehearsing the same steps our world once took. And perhaps on one of those distant worlds the transition has already happened.